All right, here we have my foam glass. That's the material I have searching for so long. It seems to fit all the requirements for the displacer body. Last year I made it in stainless steel, and it was my thought was it should fit this tank. It was every welding points and so on was, I mean, it was rather heavy and expensive materials, difficult to prototype and so on. And then I suddenly come over this material, who seems to be much better. It's very lightweight material. It's cheap. It's possible to shape, as for instance this dome form. I will have the top side here of the tank shaped with this, and it's the half the weight as this one, and I will build and body similar to this, but dome shaped. I will punch small holes where the air will flow from the top side. The top side will be 300 degrees, like this. So I will have the cell foam like this, and I will punch hole through, hot here, and there will be water here, there will be a plate weld here, and pipe here, and also a float here who compensate the weights of this. And underneath here we have the water will go up and down here, and we will have the water go in and out, and here we have some sort of hydraulic output and input extraction of the power, but that's another issue. We concentrate on this. So the heart of the Stirling engine is this. Here we have the cell glass, and here we have the honeycomb structure, the aluminium foil, who actually goes ups and downs in the water and have make very many cylinders. And if I take a history of my innovation for around 15 years ago, the first thing I was innovated was if you look at the traditional so-called Ringbom Stirling engine, you have a displacer body, you have hot side here, you have a rod here to outside the outside the air here, and you have an output here, and you have some sort of working piston here who collect the and some crankshafts. This get out the power. And the Ringbom is actually that when you move up and down this, when you move this up, you the gas go from the air go from cold side to the hot side, increase the pressure, and it will suddenly push this rod. The crucial thing is that you need to do is you want low friction here, but you also want no air leakage, and that is somehow a bit challenging to do. My innovation was I flip this Ringbom upside down like this. Sorry. We have our water surface. We have our displacer. We have our Ringbom. And here we have a plate. And we have water. Here is water also, just for ventilation. And now it is not crucial at all, this precision. You can have very lows here because it's underwater. So that was my first idea. No one ever have done that before. And the next thing was that, and then you have, of course, a pipe here, for instance, and check valves and so on, who take out the output powers. But that's another story. The next idea I get, when I start to do this, I figure out that when the displacer body hit the water surface, is tend to stick on the water surface. And then I do this pointed form of, and then it was just release easy from the stick effect. So in this configuration, it's hot up there and cold water here. And there is a wall here who separate. And if you drive very low temperature differences, it starts at 10 degrees differences without any problem. If you have low temperature differences, then you may have a larger diameter here to make it force up and down. So that was the two first innovation. And then the obvious thing was to put in isothermalizer plates, but that's already innovated in the old fluidine engine. The nice thing with this called Ringbom, classic Ringbom. Configuration, and this is let's say Water Welin Ringbom configuration or something, I don't know. Anyway, I have only seen two guys who have so far have replicate my idea, and it works just fine. It was very easy to do. So and if we go back in the history regarding fluidine engine, what is that? Well, that is a huge U-tube like this. You have a hot here chamber, cooled, and you have the regenerator here. You have a water column who have an oscillation here. You have isolation body, and you have isothermal plates here, just like this. These, and then you have an output and input hydraulic pipe with the check valves and so on. I could write it like this instead. So that's the fluidine Stirling engine. The pity thing with this is that you set the frequency with this shape, and it tends to be very large column of water. In my innovation, you get rid of that. Another issue is that it moves, not discontinue. If you look at the PV diagram, pressure and volume at this axle, then you run the fluidine like this, a sinusoid. You miss this area, and that's not good. In my in my innovation, and as well as Ringbom, then you actually get closer to, I mean, theoretically you extract all these, and you can slow down the frequencies with these hydraulics. You can set the frequencies with this regardless of the size of the tank. So that's the benefit with my idea. There is the challenges is actually the displacer body. It needs to be light. It need to handle the pressure. It should not suck up water. And I think I set good hope to these materials. It was I think, deal breaker. So it will be very funny to test this. Next video I will explain the benefit of doing. Here we have isothermalizer, and why is that more beneficial than the adiabatic? Actually it depends on the so-called pressure transient heat transfer losses. That's why you need to go isothermal, as well as you want to go from that to this. You want to extract everything you can eat when you have moved your pressure to another state before you go to this state. That's why you have to do everything you can each half cycle to extract the most efficiency, even if you have 100% recycle in your regenerator. All right, that's enough for today. Thank you.